On today's episode, explosive technology could change a century of steelmaking. This episode of This Week in Engineering is brought to you by the American Society of Mechanical Engineers. Learn more about how the Society promotes the art, science, and practice of multidisciplinary engineering and allied sciences around the world at asme.org. Few materials are as pivotal in modern life worldwide as steel. The development of quantity production of iron and its evolution into commercial steel production was the enabler for the Industrial Revolution, but the basic process of iron smelting hasn't changed significantly in centuries. Iron ore is heated until it melts, and then is subjected to a reducing atmosphere where chemistry removes the oxides from the molten ore, resulting in elemental iron. The reducing agent is traditionally carbon monoxide derived from the coking of coal, a process which coincidentally took advantage of a large coal supply chain developed for the concurrent development of steam power. It also resulted in irons with a very high natural carbon content, among other impurities, requiring a second step where excess carbon is reacted out of the molten iron using air or oxygen to produce steel. Fluxing ingredients such as limestone are added to help in purification, but as an industrial process, steelmaking has not changed significantly in a couple of centuries. That may be about to change. The South China Morning Post has reported the development of a novel steelmaking technology which, if commercially feasible, could radically change the way steel is made. Known as flash iron making, the method is reported to change the 5 to 6 hours needed for smelting into 3 to 5 seconds, according to project team lead Professor Zhang Wenhai, a researcher at the Chinese Academy of Engineering. His team's research was published in a peer-reviewed journal, Non-Ferrous Metals, in November. The process is reported to work well with low and medium yield ores, which are abundant in China. Now, little is currently known about the details of the process, but it's conceptually simple. Iron ore is pulverized into a fine powder, sprayed into a reaction chamber containing a reducing atmosphere, and the resulting chemical reaction occurs explosively, resulting in a stream of molten iron which could conceivably be a continuous process rather than the batch production of current technology. The novel process takes advantage of the natural physics of finely powdered solids. The smaller the particle size of a solid substance in a chemical reaction, the higher the surface-to-volume ratio, dramatically speeding the reaction rate. It's a phenomenon well known to safety regulatory agencies like OSHA, where finely powdered substances from grain dust to polymer powders have been known to cause highly damaging explosions on farms and factories. Simple dust can be similarly dangerous inside electrical panels, and industrial users of metal powder bed 3D printers must now have approved ventilation systems in many jurisdictions. Now, in these cases, the action is oxidation rather than reduction, but in both cases, the extreme speed of the reaction makes it explosive in nature. The intriguing aspect of the new smelting process is that in theory it should be highly scalable up or down. Smaller ironworks may be just as economically viable as huge mills, and if hydrogen is used as the reducing agent, the need to move large quantities of metallurgical coal and establish large coking ovens to process it may be eliminated. There are obvious environmental benefits, but also geographic ones. Smelting operations are generally located close to large bodies of iron ore, metallurgical coal, or along major waterways where bulk quantities of these inputs can be economically shipped. Powders, however, can be bulk transported by rail and can be fluidized for relatively easy handling. Hydrogen gas can be made from electrolysis or derived from hydrocarbons and can be piped. In theory, this process would allow iron smelting almost anywhere there is efficient rail transportation or access to piped hydrogen or natural gas. Higher value steelmaking, primarily electric arc mini mills, might be able to pair these small-scale smelting operations with conventional scrap processing, turning mini mills into small analogs of major steel mills. This may allow those smaller operations to profitably move down the value chain into commodity steels, improving profitability and decentralizing production of basics like structural shapes, creating a more resilient supply chain. The possibilities are endless if the economics align. And for the economics to align, cost-effective means of hydrogen gas production must be developed, and critically, the cost of pulverizing iron ore and classifying the fines, then safely and economically shipping them to the smelting site must be developed. It won't happen tomorrow, and it may not happen at all, but if it does, primary steelmaking might come to any town or city, anywhere.